In this video, I'm going to talk about reinforcement learning. Reinforcement learning is one of the most exciting fields of machine learning today, and also one of the oldest. It has been around since 1950s and producing many interesting applications over years, especially in games uh, and in machine control, but seldom making the headline news. But a revolution took place in around 2013 when researchers from an English startup called DeepMind demonstrated a system that could learn to play just about any Atari game from scratch and eventually outperforming humans in most of them using only raw pixels as input and without any prior knowledge of the rules of the games. So, how did they do it? With hindsight, it seems rather simple. They applied the power of deep learning to the field of reinforcement learning, and it worked beyond their wildest dream. So, here I'm going to tell you only about the basics of reinforcement learning and basically the grounds which all these amazing breakthroughs were built upon. In reinforcement learning, a software agent makes observations, and this is basically the agent here, and take actions within an environment. This is the environment when the agent takes some actions. Uh, and in return, it receives some rewards. And the objective here is to learn to act in a way that will maximize the expected long term rewards. And you could think of a positive rewards as pleasure and negative rewards as pain. And this is something that you need to know, that when we're talking about reward, it could be misleading because it has a positive implication, but in this case it could be both positive or negative, so both pleasure and pain. In short, the agent acts in the environments and learn by trial and error to maximize its pleasure and minimize its pain. And this is quite a broad setting which can apply to a wide variety of tasks. I give you some examples here. For example, the agent can be the program controlling a walking robot. In this case, the environment is the real world. The agent observes the environment through a set of sensors such as cameras, touch sensor, and its actions consist of sending signals to activate motors. It may be programmed to get positive rewards whenever it approaches a target destination and negative rewards whenever it wastes time, goes in the wrong direction, or falls down. The agent can also be the program controlling the famous Miss Pac-Man. In this case, the environment is simulation of the Atari game. The action are the 9 possible joystick positions: upper, left, down, center, and so on. The observations are the screenshots and the rewards are just the game points. Another one similar to this is, and this is example that became headlines a few years back, is the agent can be programmed playing a board game, which is the game Go here. Uh, At the same time, the agent does not have to control a physically or virtually moving thing. For example, it can be a smart thermostat, getting rewards whenever it is close to the target temperature and saves energy, and negative rewards when humans need to tweak the temperature, so the agent must learn to anticipate human needs. The agent can also observe, for example, stock market prices and decide how much to buy or sell every second. Rewards are obviously the monetary gains and losses. Now, that there may not be any positive reward at all, for example, all agents move around in a maze, getting a negative reward at every time a step, so it better finds the exit quickly as possible. There are many other examples of tasks when reinforcement learning is well suited, such as self-driving cars, placing ads on the web pages, controlling where an image classification system should focus its attention. So what is the difference between reinforcement learning and our standard machine learning problems? Let's give the example of classification here. In classification, we have a set of training data and a model for making a single prediction or decision. And this is how it happens. We give the training data to the classification algorithm. It builds a model for us, and based on that model, so we already have a model set. Whenever we get a new data point, we input it to the model, already trained model, and then we get some predictions which we will use basically for our needs. And now, before getting to reinforcement learning, let's think about the animal or human learnings as well. And let's again take the classification examples. Basically, how to classify a new given input, how to give the y new label to it. We do two-way. We either do it by memorization, so we have seen something before. By seeing it again, we say, oh, it's again what we saw before, and yeah, I know how to classify them. Or it is procedural learning, and by that means that we interact with the environment. We do something, we realize it was wrong, and uh, basically we learn by making mistakes. And if I want to give you a bit more on the procedural learning, basically it is learning how to act to accomplish goals. And here we have an environment that contains reward. It's like a kid touching the fire. It burns and it's a negative reward, and we don't touch it anymore. And learn is a plus policy for acting. And there are important differences from classification here. For example, one is that you don't get examples of correct answers, and you have to try things. And the idea in the reinforcement learning as well as the procedural learning is somehow to find this good policy, to learn this policy of actions that gets us to the reward we are foreseeing. As you see, for example, in this example, there are several different paths that this robot could take to get to this pot of gold, but which one is the most optimal one and which one is giving me the highest reward? Probably you see, there are some blocks also in this grid. The robot could get and could choose a path and then get a stock uh, in a corner that there is no way I'm getting to the pot of gold. And there are some other important observations. You need to know what you know matters. And what do I mean by that? First of all, the question is, do you or the agent know the environment? What are the effects of the actions? What are the rewards? What are the penalties that are negative rewards in a sense? And if yes, if we know everything about it, then we can use dynamic programming. We don't necessarily need to use reinforcement learning. And what does dynamic programming is basically, it's like planning than learning. And it is about value iteration, policy iterations. So we do some sort of optimization to get where we are. And this is happening when we know the environment, we know the reward, we know the effect of the actions. If no, and this is where the reinforcement learning comes into play. We can use reinforcement learning and acting and observing in the environment and learning from the observation. Reinforcement learning shapes behavior using reinforcement agent takes action in an environment, and those actions change the state and then trigger the rewards. Through experience, an agent learns a policy for acting given a state, choose an action, and then maximize the cumulative reward during an episode. Interesting thing about this problem is that it requires solving credit assignments in a sense. What actions are responsible for a result? And it requires both exploring and exploiting. Do what looks best or see if something is really best. So basically, if you want to be a bit poetic, you shouldn't cover the book by the judge. What did I say, really? We shouldn't judge the book by its cover. That was totally off what I said. And yes, so we need a bit more interaction with the environment. So that is where the policy search concept comes in. And what is policy search? It is the algorithm used by software agent to determine the action, and that is called policy. For example, the policy could be a neural network taking observations as input and outputting the action to take. The policy can be any algorithm you can think of. It does not even have to be deterministic. For example, consider a robotic vacuum cleaner whose reward is the amount of dust it picks up in every 30 minutes. Its policy could be to move forward with same probability every second, or randomly rotate left or right with probability 1 minus p. The rotation angle would be a random angle between two different values, and since the policy involves some randomness, it's called a stochastic policy. The robot will have an erratic trajectory, which guarantees that it will eventually get to any place it can reach and pick up all the dust. The question is, how much dust will it pick up in 30 minutes? How would you train such a robot? Like, how would you train your dragon? There are just two policy parameters you can tweak, the probability and the angle range. One possible learning algorithm could be to try out many different values for these parameters and pick the combination. Uh, I have it here, and pick the combination that performs best. This is an example of policy search, in this case using a brute force approach. However, when the policy space is too large, which is generally the case, finding a good set of parameters this way is like searching for a needle in a gigantic haystack. Another way to explore the policy space is to use, for example, genetic algorithms. So there are different ways of looking for the optimal policy. There is another approach that use optimization techniques by evaluating the gradients of the rewards with regard to the policy parameter, then tweaking these parameters by following the gradients toward the highest rewards. And this approach is called policy gradients. Uh, so what are the types of reinforcement learning out there? We have three of them: search-based, model-based, and model-free. Search-based learning is basically evolution directly on a policy, for example, genetic algorithms. This is what I was just explaining. Model-based is to build a model of the environment, and then we can use dynamic programming. And this is a memory-intensive learning method. And there is another one which is called model-free learning, and in this way we learn a policy without any model. And it requires limited episodic memory, though more helps if you have. So let's focus on this model for a free policy because it seems to be one of the best ones. So one is the actor-critic learning, and this is a temporal difference method version of the policy iterations. And what's happening here is basically there is a critic that says whether an action taken is good or not. And the other one is Q learning. So what is Q learning? Let's give you some definitions here. First of all, we have the current state and the current action A. And then we have a transition function. Given the current state and given the current action, where do we lead? Do we get to what is our next state? And sometimes the next state is actually the current state, so we loop in the same state. And what is the reward if I basically take this action in this given state? And then we have a policy. As you have already seen, we discussed about what a policy is. And then the Q function is basically Q learning is basically the Q function, sorry, is a value of taking action A from state S. So what does the Q function does? A Q function estimates the discounted cumulative reward started in a state S, taking action A, and following the current policy after that. So suppose we have the optimal Q function. What is the optimal policy in a state? And that would be the action argmax B of Q, S, and B. But the thing is that we don't have the optimal Q function at first. We could act as we do and then update the Q function after each step so it goes closer to the optimal Q function. And eventually it, of course, will become optimal. But then sometimes it's not really the plain reinforcement learning is not the answer. I'm not going to through that here, but this is more or less why the deep reinforcement learning started playing a role, because it would get you to the optimal, much closer to the optimal than the original reinforcement learning models. So how this this Q function is going to be updated? The basic update equation, the very basic one, is this. Basically, the value is getting to be updated by the reward uh, of taking action A at state S, and the maximum B of QS prime and B. But there's a catch here. We sometimes need to add a discount factor. And what does that mean? That actually means that uh, the later you get the reward, it has less of an impact. So we add some a discount to the maximum reward that you can get. And with the learning rate for non-deterministic worlds is also going to change. So if we are moving to an undeterministic world, then we need to add the learning rate to the whole story as well. So we both have the discount factor and we have the learning rate starting playing a role here. Uh, let's look at this example. This robot wants to get to the pot of gold here from, so basically what we know is that the Q function on this state, which is here, and the action of going to right will get you to the pot of gold. If it was on top, so basically it's going backward. What are the possible ways of getting there? One from the first one is going down, and then here, so we have this, we already started adding this discount factor, and then again and again. So there is a path. The furthest this is, the highest the discount value will be. So this is another way, this is exploring different paths to get to the pot of gold, to find the optimal uh, way of doing certain actions. So this is what takes us to the explore versus exploit trade-off. The fact is that we cannot always choose the actions with highest Q uh, values. The Q function is initially, as I said, unreliable, so we need to explore until it is optimal. And one of the most common methods is epsilon greedy, and here basically we take a random action in a small fractional steps, that is epsilon, and we decay epsilon over time. Uh, there is some work on optimizing exploration, but people usually use this simple method. Under certain conditions, Q learning will converge to the correct Q function. And this is basically when first the environment model doesn't change, the states and actions are finite, rewards are bounded, learning rate decay with resisted state action pairs and exploration methods would guarantee infinite visit to every state action pair over an infinite training time. But there are also some challenges when we're dealing with reinforcement learning. First of all, a reward design could be very involved. Uh, we could have online learning, no time for tuning. We could have continuous feature. We could have delayed rewards. So this makes the whole reward design quite complicated. Also, parameters can have large effects on learning speed. Turning has just one effect will slow it down. Uh, Realistic environment also can have partial observability, and realistic environments can also be non-stationary. So these are two other challenges. And of course, another challenge which will lead to the concept of multi-agent reinforcement learning is the fact that we could have multiple agents. So in theory, reinforcement learning has a very basic concept or idea behind. Basically, you do until you learn, but sometimes you're bound by a computational complexity, the complex environment, agents, and many different things that we are dealing with. And although it's out of the scope of this course, but if you're interested in this, I suggest that you probably use more sophisticated ways of doing reinforcement learning. That is, for example, deep reinforcement learning. Okay, so let's see in the other video what other type of learnings are there that we have not talked about.